Today we do just a little bit on crystallisation when ionic compounds come out of solution and form crystals. And that happens usually when you cool down a saturated solution and too many solute ions or molecules are in solution, so they've got to come out of solution, and they do so by forming crystals. You may have done something on this earlier in the year, but just to go over the most important points. If you're wanting to make bigger crystals, what do? The best way is cooling it more slowly, or increasing the concentration just by slow evaporation. Whatever it is, you're just not disturbing the solution and giving fewer options for lots of little crystals to form. So the only way that ions can come out of solution is to latch onto the few bigger crystals that are already forming. Seed crystals is another way, providing the nuclei to start the process off. Different geometries of the ionic lattice produce different shaped crystals. So the pattern on a nano layer level, the arrangement of the different anions and cations in the ionic lattice at the atomic level is replicated in the symmetry we see in the crystals. So sodium chloride has got a cubic lattice, and if you look at salt crystals, sodium chloride crystals under the microscope, you'll also see their cubic crystals as well. Same with zinc sulfide, the mineral sphalerite. The lattice has got a tetrahedral symmetry involved. A little bit difficult to see from these two-dimensional diagrams, but when you see the mineral sphalerite, you also see that tetrahedral symmetry replicated. Okay, now we're on to the most important part of the chapter, and that is playing around with different ways of measuring concentration, different units of concentration. Now, there's a lot of sort of fairly tedious arithmetic here, but it is really important in chemistry. You really need to get your heads around manipulating quantities in this way. If you do so, it just makes life a whole lot of easier through all the calculations in chemistry. Basically, all measures of concentration are a ratio. They indicate to you the proportion of the substance that you're interested in. So every unit of concentration you come across is going to be the amount of substance on the top line. So whatever it is that the actual chemical that you're measuring, in this case it's potassium dichromate, and that's always divided by the total amount of the sample. Total amount of solution often, total volume maybe, that the potassium dichromate is dissolved in. They all work the same way. So we just have different units, different ways of measuring the substance we're interested in, different ways of measuring the total size of the sample. So if we're measuring a particular chemical, we might measure that amount of chemical in grams or moles if it's a solid, or perhaps mils, grams or moles if it's a liquid. Then that's going to be contained in a sample. If the sample is a solid, often it will be grams or milligrams that we measure it as. If the sample is a solution, it's liquid, then litres and mils, etc. are the common units. Note that the sample is always going to be a mixture. So it's impossible to measure the moles of the sample because that doesn't make sense. You can't work out the moles if it's a mixture. So the trick with these is have a look at the units. Every time you're told a concentration, you're asked to calculate a concentration, you're given the units. And it's those units that give you the formula. That's the magic trick in this stuff that makes it easy. So if you're told that the concentration of something is 17 milligrams per gram, then you know the formula that produces that is concentration equals milligrams of substance divided by grams of sample, total sample mass in grams. So straight away, once you see those units, you've got yourself a formula. Concentration equals milligrams of substance divided by grams of sample, all from those units. And you can do that with any units of concentration. So for instance, milligrams per kilo. And that's, I think, how codeine in Panadeine is expressed. 760 milligrams per kilo. What does that mean? It means this substance, 1 kilo of this substance, of this tablet, would contain 760 milligrams of codeine. That's the concentration. So that gives you the formula. Concentration equals mass of substance in milligrams divided by total sample mass in kilograms, all from the units. Concentration equals milligrams of substance divided by kilograms of sample. And in this case, because there is 1 million milligrams in a kilo, this can be expressed, can be called parts per million. Grams per litre. Common way of expressing concentrations. Concentration of salt in river water, 15 grams per litre. There are 15 grams of sodium chloride in 1 litre of river water. So that gives us the formula. Concentration equals mass of substance in grams divided by total sample volume, in this case, in litres. Grams per litre. Grams per litre. They're all in the units. Milligrams per litre. Caffeine in Coca-Cola, 105 milligrams per litre. So 1 litre of the stuff would contain 105 milligrams. Formula. Concentration equals mass in milligrams, mass of caffeine in milligrams divided by total sample volume, total volume of solution in litres. Milligrams per litre. Milligrams per litre. That's another one of the parts per million formulas, because 1 litre, if you do the conversion, equals 1 million milligrams. Now there are a few units which are percentages, and they're pretty similar, just with the times 100 to get us to a percentage. So 2.1% by mass, m/m means percent by mass, mass divided by mass of phosphate. Now it doesn't matter what those units are, so long as they're the same top and bottom. So long as we're measuring the phosphate in the same units, i.e. grams quite commonly, and the detergent in the same units, so grams as well. So again, it's the same ratio, mass of substance divided by the total mass of the sample, except this time it's percentage, so we times it by 100. Another way of thinking about it, grams per 100 grams. Sometimes that method works best. So if there's 2.1% by mass, that means there are 2.1 grams in 100 grams of detergent. That works as well sometimes. Percent by volume is exactly the same, except we're dealing with volumes, obviously. Usually mils, but can be any units of volume, so long as they're the same top and bottom. Oops. So 39% by volume ethanol in vodka means there are 39 mils in 100 mils of vodka. And again, it's volume of substance divided by total volume sample times 100 to turn it into a percentage. Now the one in which the units are specified is percentage mass by volume. And this time the mass has to be in grams, the volume has to be in mils. That's because when you're talking about pure water, 1 gram pretty much exactly equals 1 mil. So there's an easy conversion there. So percent mass by volume is the mass in grams divided by the volume of the sample in mils times 100. And that's your example. And that's the equivalence that that particular formula is based on. Now there are two things we can do. We can actually use the formulas to calculate amounts, or we can convert between units. But before we do that, we probably need to just revise our prefixes. You'll get a data book with this in it, a data sheet. I think these might be the ones that are in the Year 12 data book. You always get this information in chemistry. They're good to know those prefixes, I've got to say, because we do come across them quite often. You'll have come across all of these at some times in your life. And if you know what they mean, just it is useful. So to convert between two units, so if we've got something in kilograms and we want to convert it to micrograms, how do you do that? Well, first thing you do is work out a conversion factor based on the powers of 10, and then you multiply or divide as required. So, and just remember, if there's 1 megalitre, it's a huge amount. A megalitre, 10 to the 6 litres, a huge amount of water. If you want to know how many millilitres there are in a megalitre, well, a millilitre is a tiny little amount. There's going to be a huge number of millilitres in a megalitre. So if we're going from megalitres to millilitres, we're going to multiply. Large units to small units, we multiply. And if we're going the other way, there are going to be many fewer of the big unit. So if we're going from small to large, we divide. So convert 5 milligrams to kilos. First of all, our conversion factor. So we're going from milli, 10 to the minus 3, to kilo, 10 to the plus 3. How many powers of 10 difference is that? Clearly 10 to the power of 6. Always express that as a positive power. So it's like there are 6 difference between them. 10 to the power of 6, that's our conversion factor. Then we're going from a small unit to a big unit. 5 milligrams isn't much. There's going to be even less of a kilo in that amount, so we are going to divide. So it's going to be 5 divided by 10 to the power of 6. Now you'll do this on your scientific calculator and you'll get it in exponential form like that, scientific notation. It's how we expect to see it. 0.064 gigalitres to millilitres. What are we doing? We're going from giga, 10 to the 9, to milli, 10 to the negative 3. How many powers of 10 difference is that? All the way down, 9 to negative 3 is going to be 10 to the power of 12. This time we're going from a big unit to a very small unit. We're going to have a huge number of millilitres. So we are going to multiply. So 0.64 times 10 to the power of 12. Do it on your calculator, or you can do this one in your head really, and express it in correct scientific notation. Last one, watts to megawatts. So what's the prefix for watts? Well, that's just the base unit. So that's 10 to the power of 0. We're going up to mega, which is 10 to the power of 6. So the difference is 10 to the power of 6. This time we're going from a small unit to a large unit, so we will divide. So 4,500 divided by 10 to the power of 6 gives us that. Have a go at those questions. And submit your answers online. Oops, those answers weren't supposed to flash up there. Okay, now we're going to convert between, we're going to use quantities to work out concentrations. So we know we've got 12 grams of sodium chloride. That's our substance. That's the substance we're interested in. A version of that is always going to go on the top line. Then we've got a total amount of a sample. That's 750 mils of salt water. That's in various forms, that's going to go on the bottom line. So we need to get our formula. So percent by mass is, of course, mass in grams divided by volume in mils times 100. Then we substitute in. And what are we given? We are given mass in grams of sodium chloride, that's nice and easy. Volume of the sample in mils, that's even better. So just substitute straight in. And multiply by 100 and you will get the answer, 1.6% by volume, mass by volume. Now our next one, it's similar units, but this time instead of being mass by volume, it's mass by mass, percentage by mass. So the top line's fine. We've still got our 12 grams of sodium chloride, but the total sample mass, 750 mils, we've got to convert that to grams. Now, of course, we know that 1 mil for dilute solutions, it's true enough, 1 mil weighs 1 gram, so if we've got 750 mils, we've got 750 grams, so we're substituting 12 and 750 again into our formula, and surprise, surprise, we get the same result. Parts per million, as in milligrams per kilo. So that's milligrams of substance, sodium chloride, divided by kilos of solution. Now what do we know? We know that we've got 12 grams of sodium chloride. We need to convert that to milligrams. So we times by 10 to the power of 3. So that's our mass of sodium chloride in milligrams. What about our sample mass in kilos? Well, from the previous step, we had our solution weighing 750 grams. We need to convert that into kilos. So grams to kilos is divided by 10 to the power of 3, 0.75. Now we just plug those numbers into the formula, and what do we get? 16,000 milligrams per kilo, which is 16,000 parts per million. Of course, we can use the formulas the other way around. Volume of 64 grams per litre glucose contains 50 grams of glucose. Mass of glucose in grams from the formula divided by volume of solution in litres. Now what do we know? We know the concentration is 64. We know the mass of glucose, the substance, is 50. Sub in. Then we've got to transpose to solve for volume. When we do that, volume goes on the top line over the other side. The 64 comes down to the bottom side on the other side. We end up with V equals 50 divided by 64. And we get 0.781. Of course, from the units, we're told that has to be litres because that's the units in the units of volume in the formula. And you would commonly convert litres into millilitres. Well, volume of ethanol is present in this 375 ml can of 3.5% by volume rum and cola. Okay, so the percent by volume. So the formula is volume of ethanol on the top line, volume of rum and cola on the bottom line, times 100 because it's a percentage. So we know the concentration 3.5, we know the total sample volume is 375, we solve for volume. 375 goes over the other side, multiplies, the 100 goes over the other side and divides. We end up with 13 mils. Okay, have a go at those questions and submit your answers online. Okay, once you've done that, that's ready for the next small segment of the Chapter 14 review. So check Google Classroom for when that is going to be due.